Easy Physics Exercises with Dr. Ken. This is number 9, three-phase star or WYE in AC circuits. So let's get into our first exercise. 9.13. A three-phase distribution transformer is star connected and the supply line voltage is 440 volts. What's the transformer's phase voltage? As I always say, draw the circuit. Get it clear in your head. So I've drawn the circuit and I've put the little bit of data that they've given us. So we know it's star connected, so star drawing, we know the line voltage is 440 volts. And we know we want to find out the volts phase. So we know that there is a √3 relationship between those two things. So this being the volts line. So volts phase is simply the volts line divided by √3. So we can take our 440 volts, we can divide it by √3, giving us 254 volts is the phase voltage. So that's the voltage directly across the phase. 9.2, a three-phase star-connected 4-wire supply has a phase voltage of 110 volts. What's the line voltage? Again, draw the circuit, and basically this is almost the exact opposite to what we've just done. So they've told us that we have 110 volts, and that's our phase voltage. So our phase voltage, and that's this one here. And we need to know what the volts line is equal to. So in this particular case, volts line is the volts phase multiplied by √3 this time. So 110 multiplied by √3 tells us that 191 volts is our volts line. Moving on to number 3, 9.3. A star-connected induction motor is connected to a 600 volt supply. The motor takes a line current of 52 amps from the supply. Calculate the impedance of each phase. So this one's going to be a bit of a two-step process. So again, draw the circuit diagram and put on it the information that we've got. So we've got 52 amps and we've got 660 volts, and that's volts line. But to find out the impedance across just one phase, we will need to have I phase, but we'll also need volts phase. Now we already have I phase because in a star connected system the current is in series, or the windings I should say are in series, so the I phase and the I line are the same. So the 52 is both the I line and the I phase. But we're going to need the volts phase, so that's what we're going to do here. So volts phase is simply the volts line divided by √3. So 600 divided by √3 gives us 646 volts. So that's our voltage across a single phase. The next thing we need to do is to get the impedance, and that's just nice Ohm's law. As long as we have the volts phase and the current phase, we can do that. Now we've just calculated the volts phase at 346. If we divide it by the current, 52, that's going to give us the impedance. So we end up with an impedance of 6.65 ohms. So that's the Z phase for our winding. (9.4) A star-connected symmetrical three-phase load takes 12 amps from a 220-volt three-phase 4-wire supply. Calculate A, the impedance of each phase of the load, and B, the line voltage. So the question says symmetrical, and what they mean is symmetrical. It means it's the same, so all three phases draw the same current. So again, we draw our circuit diagram, we label it with what information that we have. So they told us we have playing with 12 amps, and three-phase load takes 12 amps at 220 volts, three-phase, 4-wire. Calculate A, the impedance, and the line voltage. So they've given us the phase voltage up here at 220 volts. So it's not too difficult to work out the impedance straight away. So the volts impedance, because it's a star circuit, this current is both I line and it's also I phase. We can simply go 220 divided by 12 is 18.3 ohms. Next thing they asked us to work out was the voltage line, and if the voltage phase is 220, then it's simply 220 multiplied by root 3, giving us 381 for our volts line. So 9.4 on the diagram below, demonstrate the connection of a motor in star to a three-phase supply. This is reasonably straightforward, and you can see the A1, got a winding across here, a winding across here, and another winding across here. But you'll notice all the starts are on the bottom, all the finishes are on the top, so it's actually quite easy to connect it in a star configuration, and we simply join all the finishes together, and then we supply a phase to each of the others. Simple as that. So that's a star connected. Motor terminal boxes are very well set up. They're always set up in this configuration, allowing you to put links straight across and connect like this for a star. If you need to go a delta, you can just connect the links vertically. (9.5) now, a three-phase star-connected heater is connected to a 440 volt three-phase 4-wire supply. If the resistance of each heater element is 14 ohms, then determine the magnitude of the neutral current. Hint, hint, hint. Draw the phasor diagram and add all the currents together. So you can see here I've not only done a phasor diagram, I've also done an ordinary diagram. So the phase voltage, volts phase, is going to be 400 divided by root 3, giving me 231 volts, because they gave me the line voltage at 400. Then I could work out the current. So the current is 231 volts divided by the 14 ohms, which was the impedance of the windings, giving me 16.6 amps. Now they're all the same, and I need to add them up together. So over we go from here to our phasor diagram, and I simply drew in the three currents. So 16 amps here, 16 amps here, and 16 amps here. I then did a phasor addition of B and C. So this is B, and this one was C. I did a phasor addition and ended up with the green arrow through here. And then finally, I simply added the green arrow here by taking it top to tail, and it brought me straight back to this point here, which is 0 amps. So because they're all at 16 amps, A plus B plus C, and they're all at 120 degrees, therefore my current must end up being 0. So in this particular case, IA plus IB plus IC comes to 0 amps. All three phases added together come to 0. So 9.6, a three-phase, four-wire supply has the following connected. On A phase to neutral, 4 amps resistive load. B phase to neutral, 3 amps lag at 60 degrees, and C phase neutral, 3 amps lead at 50 degrees. Determine the value of the neutral current and its direction. So first thing I've done now is I've added in the B phase. And remember, our rotation is anti-clockwise. So my phasor diagram is rotating anti-clockwise, and I had B at 3 amps lag. So there's my 60 degrees in here, and it's lagging the B. The next thing I have to add is the C phase, and remember the C phase was a lead. Turn my pen on again. So 3 phase was 50 degrees lead again. Phasor rotation is in this direction. So here's my C at 50 degrees lead, also at 3 amps. So I now add in my B, so that's what I've done here. Just get my pen up again, and I've put in B. So all I've done is taken the length of B here with my compass, put the point of my compass on here, and I've scribed an arc to give me that point there. I do the exact opposite with 50, and I end up with this parallelogram effect. Now all I have to do is draw in my phasor like this, and there is my B plus my, drew that too far, B plus C. Remembering over here, we'd already put A in as resistive. So there's my B plus my C. Now I need to add my B and my BC that's already been added needs to be added to my A. So here's my A being put in, so there's the A phasor. Simply picking up the A phasor horizontally and putting it in. There's the green phasor, which was the addition of BC. So that's this one here. This is there's my B plus C being put in. And I've ended up with this point here. The result for its magnitude is this one through here. So we've now got our current's magnitude, but don't forget, when we're doing currents, the final result is actually 180 degrees the opposite way. So we actually want to subtract all the currents by adding them all up and then reversing the final answer by 180 degrees. So my final answer should end up out here. So there's my final answer. The current in the neutral scaled off is about 2 amps. It's at minus 16 degrees from the reference. So that's that angle in there. And again, remember we're rotating this way. So it's behind, so it's minus 16. So don't forget, you go A plus B plus C, but we always reverse the final result for when we're determining neutral currents, because we actually want to get the opposite. By adding, we actually end up subtracting. So on this one, 9.7, a 3 single-phase 240 volt loads are connected to different phases of a 415 volt 3-phase 4-wire supply. Determine the value and direction of the neutral current, again, if A phase has a capacitor run taking 11 amps at 0.91 lead, B has a split phase motor taking 15 amps at 0.66 power factor lag, and C phase has a 2.4 kilowatt radiator. So we're going to have to turn those power factors into degrees so we can put them on our phasor diagram. So the first one is our A phase. I just turn the pen on and it comes out at 26 degrees. Of course, if I take cos, remembering that power factor is always the cos, but if I take cos to the minus 1 of 0.95, it's going to give me 26 degrees. So it told me it was leading by that 26 degrees. So its length, the length of the phasor, this bit here, its length is 11 amps and its angle in here is 26 degrees. So I've got my first phasor on the drawing, or on the phasor diagram. So the next one is we're going to put the B phase. This time we've got a power factor of 0.66, and again cos to the minus 1 tells me it's at 49 degrees, but this time we know that it is lagging. So it's lagging the B phase. So again, remember it's rotating in this direction. So the lag angle is in here. So there's my minus 49 degrees. Our next step is to add our third phasor in, and this time it's nice and easy because they tell us that the C phase is a radiator, but they don't tell us how many amps. They tell us the kilowatts, and we know it's a single phase at 240 volts, so it's pretty easy to work out the kilowatts, and you can see I've done that here. The current is simply the power divided by the voltage, gives me the current in amps. In this case, 10 amps, so the length of my phasor is scaled out at 10 amps, and its angle is 0 degrees. So the angle is 0 degrees because it's in phase with the C phase. Now we've got to start adding them all up together. So our next step is we're going to add the current in the C phase to that of the B phase, and I've simply taken my compass, measured the length here, so I've simply measured this length, then put the point of my compass here and scribe an arc out here somewhere. Next step, do exactly the same again and measure the length here with my compass, put the point of the compass on here, and then scribe an arc, and where those two arcs cross, back to the origin, and that will give us our B plus C currents. And you can see I've put that in as a green phaser now so you can see it quite clearly. Finally, we have to add the green phaser and the red phaser. So again, get your compass out. Measure the length of this phaser, put the point of your compass here, and then scribe an arc out generally in this direction. Got a rough idea where it's going to end up. Then next, we do the same again. Take a pen, sorry, not a pen, take a compass and measure this one, put the point of the compass up here on the end and scribe an arc. And where you've scribed the two arcs, sorry, I've got my arcs in the wrong direction. Arcs end up here, and we end up with a phaser in here. Don't forget that that's not the final answer. Remember, we're adding up the neutral currents so that we can end up knowing what a final current is. Remember, we want to get out here at 180 degrees. So you can see there, my final current is that length. So the length is reasonably obvious. But don't forget, like I said, we're going to have to project that length out here at 180 for our final answer. So there it is. I scaled it off on my drawing at 12 amps at minus 50 degrees. Why minus 50 degrees? I'll explain that again. The minus 50, it's the angle in here back to the reference. So there's the final thing. And that's at minus 50. Only after we'd rotated our final answer through 180. So now we're up to 9.8. Determine the load star point to neutral voltage of a 400 volt 3-phase 4-wire system if the following voltages are measured when the neutral is disconnected. So when the neutral is disconnected, a phase to star point of 210 volts for A phase, B phase star point to the neutral is 155 volts, and phase to the star point is 270 for the C. Now the trick here is not to use those voltages immediately, but to draw your phasor diagram with your standard voltages. So they told us that the normal voltage is 440 volts. So you actually need to draw your phasor diagram with your phase voltage, showing the 120, even though our final phasor diagram certainly won't be 120 between each phase, but we begin with 120 degrees between each phase. Now each of those phases is actually at 230 volts. So they've given us the line voltage, so we need to find out what the phase voltage is, and the phase voltage is 230 volts in this case, because we're going to take the 400, we're going to divide it by root 3, which gives us 230 volts. So at this point, it's important to understand that this phase length is 230 volts. The angles between all the phases in here, they are all at 120 at this point. So our next thing is to take the A phase and get your length on a compass. It's important you do this with a compass and you do it accurately. So we've scaled this phaser out here at 230, but it tells us that the A phase voltage when the neutral is disconnected is 210. So you set your compass to 210 in length, and you can see that somewhere out here, you're probably not going to be able to tell straight away, but you're probably going to have to draw an arc that kind of follows out here. It's going to be in this kind of space, but we don't quite know where yet. The next is to do the same with the B phase. So here's the B phase, and again, this phaser here is the B phase length at 230 volts. But we set our compass now to 155 volts on our scale. And then we scribe another arc out here with it. And we previously scribed an arc out there kind of thing. And it's pretty obvious that we're going to kind of end up around this point eventually. The next trick, or the next part of the problem, is to finally take the C phase, do exactly the same thing again. So set your compass to 270 degrees on the scale, put the point of your compass up here, and then scribe another arc. So we will end up basically with 3 arcs which come very close to connecting to each other, and that center point is the neutral voltage, or that point. So it's here's neutral, it doesn't change, but because we've disconnected our star point from the neutral, our star point, I'll just call it SP, has now drifted away from here. So here's the voltage in here, and that's its angle. So you can see here, the neutral always stays in the center of these voltages that are balanced, but we've now got the out of balanced voltages scribed in, and we now know that that point there, just simply scaled off the drawing, the volts at the star point is 70 volts. And that's simply the length of that phaser. So that is our 70 volts. That's how we get it. So just to clarify again, you've got to set up your original phasor diagram at 120 with the original voltages before the neutral became disconnected. Then once the neutral did become disconnected, you then use those voltages and you just scribe in arcs until you find approximately, it's only ever going to be approximately, the point where the star point voltage has ended up. So let's go on to 9.9. We've got a 32 ohm heater elements are connected in a star to a 415 volt 3-phase supply. If the fuse to the C line blows, determine the load phase voltages and the line current for a 4-wire system and a 3-wire system. You're going to have to draw the diagrams for this. This is a little bit tricky. So here's the first one. 3-wire, so there's no phase relationship, so we're going to have to use Ohm's law. And I'll show you how we did that. So here's our star connected system. I've labelled the 32 ohms for each of the phases, as you can see, and we've got 415 volts. But the B phase here, open circuit. So this one is 0 volts, nothing here, and we've got 415. Because of this arrangement, there is no phase relationships. It all goes out the window. So we're simply going to use Ohm's law. So the current is simply the voltage divided by the resistance. Now the voltage across any part of the circuit, and the only part of the circuit that's actually going to have current through it, by the way, is going to be this one here, because it's the only one that has voltages across it. So the voltage across there is 415 volts, so 415. So A to B, 415 volts. The resistance is the addition of the A phase and the C phase. So 32 plus 32, of course 64. So 415 divided by 64 gives us a final current of 6.48 amps. So that's it for a 3-wire system. So what happens when we have a 4-wire system? It's a little bit different. It's similar, but a little bit different. Let's look at our second diagram here. And you can see I've now included the neutral. We've still got 0 volts here, open circuit, 415, 415. But because the neutral is present, we're still going to get current, possibly through here, and current also possibly through here. Well, we are, because it's out of balance. So in a 4-wire neutral present, so the phase voltages are there. Because this neutral is here, volts phase is also here. So we're going to have to work out what volts phase is. So volts phase is the voltage line divided by root 3, 415 divided by root 3, we've got 240 volts. So our phase voltage is 240 volts. And it's only present because we have a neutral. So finally, the current in the phase is simply going to be our 240 divided by 32, giving us 7.5 amps in each of the phases. So we're going to get 7.5 amps flowing in each of these, and much of that will flow into the neutral because it's out of balance, because this particular winding has been taken out because there's no voltage connected to it. So I hope you've enjoyed some problem solving around 3-phase star connected systems.